Welcome back. This is the continuation of part 1 of 3x problem. In this part, we are going to see a beautiful way to solve the original problem and we are going to get the solutions. But this is going to be a lots of paper and pen work, so let's get started. In the part 1, we have considered some simple scenarios up close to see through the students' thinking at each step. Now let us take a different perspective. As we have seen, each student reduces their number to two possibilities. This is based on the fact that one of their numbers is the sum of the other two. So each student maintains a set of possible values that his number can be. So let us call them as can be sets. Let us call the sets as T of A, T of B and T of C, corresponding to Albert, Brinda and Cain respectively. So T of A, T of B and T of C are can be sets of Albert, Brinda and Cain respectively. The set TA is this, the set T of B is this, the set T of C is this. Now if a student can eliminate one of the possibilities from his can be set based on the previous conversations, then he can claim the remaining possibility as his number. If he can't do that, he says, I don't know. To start with, each student knows that his number can't be 0. So the student checks whether one of his element in his can be set is 0. If it is, then he can eliminate that and tell the remaining element as his number. This is what we have seen in part 1 as if someone sees the other two numbers to be equal, then he can claim his number to be their sum. So the idea that the number can't be 0 helps in the possible elimination. So each student maintains a set of possible values that his number cannot be based on the clues from the previous conversations. Let us call them as cannot be sets. This may seem absurd, because if the student knows that his number can be any of two possibilities, then all the other numbers are in his cannot be set. But the idea is that these cannot be sets are formed and updated independently based on the clues each one is getting from the previous conversations. So at some point, some student may get one of his possible values in the cannot be set. While that happens, that student can eliminate that number, claiming the remaining element in his can be set to be his number. So let f of A, f of B and f of C be the cannot be sets of Albert, Brinda and Cain respectively. Initially f of A contains 0, f of B contains 0, f of C contains 0. So the can be sets remain the same throughout, and each student updates their cannot be sets after each conversation. When their turn comes, they check whether they have gotten one of the elements in their can be set is in their cannot be set as well. That is precisely when his turn comes, Albert checks whether T of A intersection f of A is empty set. If it is the empty set, then he says, I don't know. But if T of A intersection f of A is a singleton set, by singleton we mean a set of single element, then he tells the remaining element in T of A as his number. This is like if B minus C equal to 0, then Albert can claim his number to be B plus C. Similarly, during Brinda's turn, Brinda checks T of B intersection f of B. If it is empty set, she says, I don't know. If it is a singleton set, then she tells the remaining element in T of B as a number. During Cain's turn, Cain checks T of C intersection f of C. If it is empty set, he says, I don't know. If it is a singleton set, then he tells the remaining element in T of C as his number. Now let us see the original conversation in this perspective. Albert says, I don't know. So that means T of A intersection f of A is the empty set. Then Brinda says I don't know. So that means T of B intersection f of B is the empty set. Then Cain says I don't know. So that means T of C intersection f of C is the empty set. Again, Albert says I don't know. That means T of A intersection f of A is the empty set. Then Brinda again says I don't know. That means T of B intersection f of B is the empty set. Finally, Cain says my number is 144. So that means T of C intersection f of C is a singleton set. That is, one element in T of C is also present in f of C, which means Cain can eliminate that number. And he claims his number to be the remaining element in T of C, which is 144. Precisely, T of C minus T of C intersection f of C contains 144. This is just a set difference notation, which simply means that we remove the elements of T of C intersection f of C from T of C. So now the things are in place. Let us go through each of the conversation, and at the side we are going to maintain the cannot be sets. For each conversation step, we are going to update them. Let us begin. Initially, we know that each number is non-zero positive integer. That is, A is not equal to 0, B is not equal to 0, and C is not equal to 0. So let us update the cannot be sets. That is, f of A has 0, f of B has 0, and f of C has 0. Consider the first conversation. Albert says, I don't know. So, T of A intersection f of A is the empty set. That is this. So, B plus C is not equal to 0, and absolute value of B minus C is not equal to 0. This one does not give any new information, but this gives B is not equal to C. So B cannot be C and C cannot be B. Therefore, both B and C update their cannot be sets. So f of B includes C and f of C includes B. So this is the idea. We have to continue doing this for each conversation. Now consider the second conversation. Brinda says, I don't know. So T of B intersection f of B is the empty set. That is, we get this. Note that we have updated f of B at the end of the first step. So f of B contains 0 and C. So A plus C is not equal to 0 and C. Absolute value of A minus C is also not equal to 0 and C. This inequality does not give any new information, but this means either A minus C is not equal to 0 and C, or C minus A is not equal to 0 and C. Solving that, we get A is not equal to C and 2C, which is also C is not equal to A and A by 2. So both A and C update their cannot be sets. That means both Albert and Cain update their cannot be sets. So f of A includes C and 2C. F of C includes A and A by 2. We have to continue this for all the rest of the conversations. As the conversation goes on, we get more and more values in the cannot be sets. So we just skim over the calculation parts which we can work out easily. Now coming to the third conversation, Cain says, I don't know. So T of C intersection f of C is the empty set. This gives this, and this gives this. A plus B is not equal to 0, and B and A by 2. Solving this, we get this. So we update f of A and f of B accordingly. Now coming to the fourth conversation, Albert again says, I don't know. So T of A intersection f of A is the empty set. this gives this. So solving this as we have done so far, we get this. So we again update f of b and f of c accordingly. There are two more steps to go. Yeah, this calculation is a little bit hectic. Anyway, keeping with our calculation, consider the fifth conversation. Brinda again says, I don't know. So T of b intersection f of b is the empty set. This gives this. Solving this as we have done so far, we get this. Note that we may get repeated results, we only need to update the new results. So we again update f of a and f of c accordingly. Now we finally get to the final sixth conversation. Here finally Cain says, my number is 144. So this means T of c intersection f of c is not the empty set. There exists one element which is in both sets, which c eliminates from his can be set, that is T of c, to get 144. So either a plus b equal to this. These are the elements of f of c, or absolute value of a minus b is equal to this, the elements of f of c. But while solving a plus b equal to this, we get contradictions. For example, a plus b equal to 5b by 3 gives a equal to 2b by 3, but f of a contains 2b by 3. This, which means a cannot be 2b by 3. This leads to contradiction. Like this, these entire equations lead to contradiction. Therefore, a plus b should be 144 and the number that removed must be absolute difference of a and b. That is, we have to solve this. Solving this, we get this. In this too, there are some equations which gives contradictions, like b equal to a, which is a contradiction as f of b contains a. Removing such values, finally we get this. So there are 16 possible and feasible equations, each of which corresponds to a solution. For example, consider b equal to 2a by 3. Since a plus b equal to 144, this gives a plus 2a by 3 equal to 144. This gives a equal to 432 by 5. So one solution is a equal to 432 by 5, b equal to 864 by 15 and c equal to 144. But we need only integer solutions. So removing the possibilities which yield fractional results, we are left with just 5 possibilities. The solution corresponds to b equal to a by 3 is a equal to 108, b equal to 36 and c equal to 144. The solution corresponds to b equal to a by 5a by 4 is a equal to 64, b equal to 80 and c equal to 144. The solution corresponds to b equal to 5a by 3 is a equal to 54, b equal to 90 and c equal to 144. The solution corresponds to b equal to 3a is a equal to 36, b equal to 108 and c equal to 144. The solution corresponds to b equal to 7a by 2 is a equal to 32, b equal to 112, c equal to 144. So there are 5 solutions. But in the puzzle site, they only mentioned these 2 solutions. The interesting thing is, if we allow the numbers to be any positive numbers, which can include any fractional numbers too, then there are actually 16 possible solutions. Okay, now we got the solutions by using a different perspective. But how can we verify these solutions are actually correct? In the part 1, while considering the scenarios, we actually went through each and every step to see what is going on. In the next part, we are going to verify these solutions precisely in that way. But don't worry, we are going to do that with the computer aid. Let us end this part with this. Keep pondering. Thank you.